Hey everybody, today my audience is people that are taking abstract algebra at the university and who know a little bit of Python. And I'm going to show you how to use Python to reinforce some concepts about finite groups. And, finite groups are just groups that operate over sets, underlying sets that are finite, hence the name. And a group is an algebraic structure in which you have a set of values. In this case, their example here in Wikipedia is the set of infinite integers, so not a finite set, obviously. But the operation that they're defining for this group is ordinary integer addition, and the things that you need to qualify something to be a group are the products of associativity, which is like something we kind of learn in elementary school. You need an identity element, and an identity element over the integers on the operation of addition is just the element 0. And you need something called an inverse element. And when you're talking about addition, that's an additive inverse, or with integers, we more commonly just call it like the negative number, or the negative b for b being the integer. But I want to use Python to validate that things are groups, and in order to validate that something's a group programmatically, you do need the group to be finite, because in my Python code, I am literally gonna have a function that verifies the group properties for every member of an underlying set of a group. And this function will validate, first of all, that all the elements are distinct. And this is a little bit of a tactical Python thing, not really a mathematical thing. But then I'm going to verify closure, and this is very mathematically based. I'm going to say for A in members, for B in members, A star B, where star is our operation over the group, that A star B is also in members, and that's called the property of closure. Associativity is something that you're familiar with from elementary school, and then the identity property. Also, if you're thinking about something like the set of integers, it's something you learn from elementary school. Like for the set of integers, the identity element is 0. So if your operation is addition, and it's a little confusing here that I'm using the star, but if your quote-unquote product operation is addition, ordinary integer addition, then A times 0, which is the same as A plus 0, is going to be A, and likewise if you put the identity on the left side of the operation. And then finally, in order to demonstrate something as a group, every member of the group, which I'm going to call each member A, has to have an inverse. And in order for some other element B of that group's underlying set to be an inverse, it must be the case that B, the product of B and A, where again your operation could be like it's an abstract operation, but over Z it could be addition, not actually multiplication. That B times A equals identity, and A times B equals identity. And so for every member that I call A, I'm asserting that there's at least one member B that is an inverse of A. So my the first concrete implementation of a group that I'm going to show you is going to be written in Python, and it is going to call this verify group properties function, and it's the real simple notion of modular 3 arithmetic. So I have this little wrapper class that builds up 0, 1, and 2 as mod3 wrapped integers. And I assert that the incoming n is just 0, 1, or 2. My equality operation between two objects of mod3 just says that the underlying value of n is the same thing. And then the addition operation is the most, fundamental part of this class. I'm saying that when you add some mod3 object to another mod3 object, you sum up the underlying end values here and mod them 3. And we're just going to use the ordinary Python modular operations to do that. And I'll come back to the mul method in a second. But you can see here that I define 0, 1, and 2. I make a bunch of assertions. In mod3 arithmetic, it's like ordinary arithmetic until when adding the underlying numbers together produces something more than 3. You have to subtract off the 3. So 1 plus 2 actually equals 0. Whereas obviously under normal arithmetic, 1 plus 2 would be 3, but there is no concept of 3 in mod3 arithmetic. It's kind of equivalent to 0. And we have this little multiplication table here that I verify, and then that I verify in this doubly nested loop. But then I go on to verify the group properties. And this is when I need to come back to explaining this little mul operation. As I say here in the comment, I'm just using star as another name for plus for convenience, because if I go back to my function to verify group properties, I have you pass in members and I have you tell me explicitly what the identity element of the group is, but I assume that the members, the operation of the group is Pythonically expressed with the star operator. And of course, in order to make that happen in, whoops, I went to the wrong function. In order to make that happen in Python, you implement the special method underscore underscore mul underscore underscore. But I'll let you stare at this for a little bit, but we're about to get into the more interesting concepts here. This is just a basic arithmetic group in Python over mod3. So the interesting thing about groups is that they are, you can sometimes have isomorphic concepts of groups. And in this case, we have the notion that you can compose, you can have an operation of a group that just composes two functions together. And that composition operation over functions can have the exact same properties as like the addition operation in the simpler arithmetic mod3 group. So I have this function class here, and I initialize it with a domain. And the domain in this case is just the numbers 0, 1, and 2. So you can already see the similarities here to the group that we're about to compare it to, which was our original mod3 group. But here we're actually building up we're actually wrapping a function, not an integer. So we're passing in the domain, but we're actually passing in a function. Our equality operation simply asserts that if you're comparing two big F function objects to each other, that the functions will evaluate to the same elements over the domain. And the multiplication operation is literally the composition of the two functions from the two big F function objects. And then finally, we have this little helper here to actually call the underlying function, like self.f. And that's really mostly a sanity check. But what we have here is we have a domain, and then we define these functions: add 0, add 1, add 2. And they are literally wrapping functions. They're not directly wrapping integers, but you can see that add 0 is a lambda that applied to x basically does modular arithmetic on x plus 0. Add 1 wraps a lambda that applies modular arithmetic with x and 1, and add 2 applies modular arithmetic with x and 2. And you can kind of get a notion of what the truth table is here. And if you look at this again, it's going to be very similar structurally to these assertions here. And that gets to the notion of isomorphism. And isomorphism in abstract algebra is just a way of saying that things have equivalent structure. There's actually like a more precise mathematical definition of that. But that's what isomorphism is. And so I have created a class that is isomorphic to our simple arithmetic notion of mod3 that is using function composition. And what's kind of cool here is that, like, when I say add 2 times add 2, what I'm really saying is that I'm composing a function that has the same effect if it were to be applied to a variable as add 1. So add 2 times add 1, we know that that is functionally equivalent to the add 1 function, but we actually have to apply it to an actual integer value to get 2 in order to understand what it does. But in order to verify the group properties, you will notice that when I call verify group properties, there is never actually either an explicit or implicit call to the call method. And I'll go back there again and show you what verify group properties does. It's just literally using the quote-unquote multiplication operation, which in this case is just, excuse me, wrong file, which in this case is just function composition. Now, where things get a little even more interesting is that up here we have this like notion of a function that's very sort of like a mathematical expression, but every function over a finite set can actually be expressed as a permutation of the finite elements to an. You can think of it as a permutation of the set of elements in one order to another order of those finite elements. So what I'm using here is rot0, and that's going to be the permuter 0, 1, 2, rot1, 1, 2, 0, rot2, 2, 0, 1. And in Python, the permuter is a function that in turn returns a function, and the inner function just looks in the list that was passed in to evaluate the function. So for example, if I do rot1 on 0 and then apply rot1 to that, I get the integer 2, and that's the same as if I had applied the rot2 function to it originally. And it might take a little staring at that, but if you can understand what's happening in Python here, then you're going to understand the abstract algebra a lot better. And then these rot0, rot1, rot2 functions, I just wrap up in the same big F function object that I was using for this guy's. And add 0 is literally the same thing as rot0, or excuse me, add 0 is literally the same thing as rotate 0, because rot0 is literally just a different way of expressing this lambda function over this domain. So I verify the group properties of rotate 0, rotate 1, rotate 2 with the identity of rotate 0. And it shouldn't be surprising to you at all that these form a group, because they form a group for the exact same reason that add 0, add 1, add 2 form a group. So then after, and here I kind of make it more explicit. What I just kind of said, I say in Python what I kind of said in English, is that the function over the domain 0, 1, 2, the big F function over that domain for rotate 0 is literally the same thing as add 0. And likewise for rotate 1, add 1, etc. But then what I go on to do is I create 3 more big F functions with 3 more permuters, and I call these fix functions. In fix 0, what I'm doing is I'm saying that the value of 0 is fixed to 0, and then I'm swapping the values 1 and 2. And I could have called that function swap 1, 2, and of course it would mean the exact same thing. But in certain conventions, you focus on what value is actually fixed by the function. So the fix1 function maps the 1th element to the number 1, whereas it maps the 0th element to 2 and the 2nd element to 0. So it's effectively swapping 0 and 2, so on and so forth. And then as you scroll down, you can see that there are these 4 different groups over the 6 functions that I've defined. So there's a group over rotate 0, rotate 1, rotate 2, fix 0, fix 1, fix 2. And then there are smaller groups over rotate 0, fix 0, rotate 0, fix 1, rotate 0, fix 2. These smaller groups express the notion that, first of all, rotate 0, I should have really just called identity because it doesn't do anything to elements. Fix 0, remember, holds 0 fixed. So I'm just switching elements 1 and 2. So if I am trying to establish like the property of closure over that group, well, you know, any multiple applications of fix 0 are either just going to be the identity. If I do it an even number of times, it's going to be the identity. If I do it an odd number of times, it's going to be fix 0 again. And then down here, I give all of those 6 functions kind of a shorter name, and I build up a multiplication table just to kind of show you how these operations interact. And I think I'm going to stop here. I think I could go a lot deeper on this. So if you have any questions, just ask them in the comments. And you know, like for example, one thing I could explain is, or even demonstrate in Python is show some of the isomorphic behavior a little better between these classes. And I should point out that this particular class here with R0, R1, R2, F0, F1, F2 is a very famous class in group theory called the S3 class. It's a symmetry group. And you often see different names for these functions, and you'll even see different contexts for these functions, like expressing in terms of like rotating an equilateral triangle. So if you have any questions, just ask them in the comments, and I thank you for listening. Bye.